We're now going to connect the geometric idea of span to the algebraic idea of solving a system. So in the previous video, we talked about these two vectors u and v as an example, and they were different enough that their span was a plane. So I'm going to give you any arbitrary vector in R2. So I'm going to call it B, and it has arbitrary components B1, B2. The question we want to ask is that vector in the span of u and v? Is B a linear combination of u and v? Can I find some weights x1 and x2 to make B equal to this sum? That means we have to solve a system with vectors u, v as the columns and then B on this right hand side. We'll have 2, 1, 1, 2, and here we'll just have a B1 and a B2. I'll swap the two rows, and then I can create a 0 under that top left pivot. So I'll have a unaffected top row, and I want -2 of the top row added to the bottom row. So I'll get a 0, a -3, and then I'll have B1 minus 2, B2. At this point, I see that immediately there is a pivot in every row. I'm going to get no contradictions, and that means I am going to get a solution. I asked, could I take an arbitrary vector and write it in terms of those two components? And the answer was yes. Any vector B in R2 is in the span of these two. Now, geometrically, we know that two vectors that are air quotes different enough span a plane. And in this case, because any vector in R2 is in that span, we are going to say that the span of these two vectors is in fact all of R2. The fact that there were pivots in every row of the system with those two vectors enabled us to say any vector could be created from these, and that enabled us to say you can create any two component vector from those two. Now, just to take this idea a little bit further, here are now two vectors in R3. And the question I'm going to ask is, do u and v span R3? Can you create any vector in R3 from these two? Can I write any B with any arbitrary components as a linear combination of u and v? To answer that, we know that we have to put it into a system where u is the first vector or v is the second vector, and then we've got this arbitrary right hand side. Now, piggybacking off the last example, we are going to want to avoid contradictions. So I'll take -1 bunch of the top row and put it to the one underneath. So I'll get a 0, 1, B2 minus B1, and I'll do the same thing for the bottom row. So I'll get a 0, -1, B3 minus B1. I have a pivot there, and I have a pivot here. If I just go one step further, I'm going to try to create a 0 underneath all the pivots. Doing that is going to get me this. Now you can see that there is going to be a problem. We are going to have a contradiction unless B2 plus B3 minus 2B1 is 0. Can I write any vector B in terms of these u and v? The answer is no. Why not? Only vectors B with B2 plus B3 minus 2B1 equal to 0 can be written as a linear combination of u and v. These vectors do not span R3. And in fact, we can bring in the geometric interpretation. So remember from earlier, we said that these two vectors span a plane. The plane contains 0. There are two vectors in this plane, u and v. And the question we were asked is, can I take any vector and have it be part of this plane? And the answer is no, because look, I could draw a vector that's kind of up here in the air, and that vector is not in the plane. Those two vectors are not enough to span R3. And this is a geometric interpretation of this. If you want to span R3, I'm going to need 3 pivot rows in my system. If I take a number of vectors and I want to put them together, 2 vectors, that's not going to cut it. I need at least 3 vectors to span R3. I'm going to need 3 pivot rows. I said at least 3. I could have more. If I don't have 3 vectors, I can't do it. So in your textbook, there are these two propositions, proposition 2.3.5. If I give you a set of vectors, the span of those vectors, v1 all the way down to vn, is going to be equal to rn if and only if there's a pivot in every row of the matrix formed by those columns. So this is a bit of a generalization of what I said above. Proposition 2.3.6 says you need at least n vectors in a set to span Rn. If you have fewer vectors than that, you won't be able to span because you need to have enough pivot rows. And you have to be really careful. Some vectors will do it and some vectors won't. If I give you, for example, these three vectors, in physics, they like to call these I, J, and K. In math here, we're going to call them E1, E2, and E3. They're going to come up over and over and over again. If I were to put these into a system, you'll be able to see immediately that it doesn't really matter what I put on the other side, they will be able to span R3. There are no contradictions. I will have a pivot in every row, and any vector b in R3 is a linear combination of these. That means the span of these vectors is in fact all of R3. And there's a really easy way to see it. If I give you any vector b1, b2, b3, I have vector properties that say, you know what? You could write it like this. You could write it as b1, 0, 0 plus 0, b2, 0 plus 0, 0, b3. And that means you could just factor out those scalars in the front. This is a really easy example. We want to be able to do this for any set of three vectors, but just to try to illustrate to you what's going on, it will work this way. But you have to be careful because it's not going to work for any set of three vectors. So for example, if I were to give you this set of three vectors, I'm hoping that you could see immediately that they do not span R3. If I were to put them into a matrix for any right-hand side, you can see that there's only one pivot. V is just twice of u, and W is just 3 times u. So that really means the span of these vectors is really just some multiple of u, which is just going to be a line in R3. The number of vectors is important, but the type of vectors is also important.